Hello everyone, and welcome back to Keeping Tabs on Chemistry. In this video we're going to be talking about neutralization and titrations. Now before we can talk about neutralization and titrations, we first have to address indicators, what they are, and how they work. So a pH indicator is a chemical dye whose colors are affected by the pH of a solution, and we've talked about some common indicators before. The main ones are litmus paper, pH paper, and phenolphthalein. So litmus paper, there are two types of litmus. There's red litmus paper and blue litmus paper. So red litmus turns blue in the presence of a base. That's easy to remember because they both start with B. Bases are blue. Blue litmus will turn red in the presence of acid. So in this picture here, you can see on the top I've got red litmus paper with a drop of base. Here I've got blue litmus paper with a drop of acid that's turned it red. Now, litmus paper is actually pretty outdated. Instead, we use something called pH paper. pH paper has different colors for the entire pH scale. So it'll range from red and oranges for acids to greens and blues and purples for bases. So here are some examples of pH paper. Normally it's yellow, roughly pH 6 to 7. If I dip it in something very basic, it'll be blue, ranges of green for the less basic things. And then as we become more acidic, we go from yellow to orange to red. So pH paper is much more useful for us because it'll tell us a better, or give us a better idea of what the actual pH is, instead of just, is it an acid or is it a base? Now, phenolphthalein, unlike the papers, this is a liquid indicator. So phenolphthalein has two different forms. The colorless acid form, notice here, oops, um, all of these oxygens, they're either missing or they do not have a hydrogen. But when they are hydrogenated, so when they all have OHs instead of just O's, then it turns pink. It's a difference in chemical structure that causes us to see a different color. So the pink color happens when we're in the presence of a base. The colorless form happens when we're in the presence of an acid. So you can see in the bottom right, there's a picture of during a titration what you might see when it reaches roughly neutral, kind of halfway between its colorless and its fully pink form, that light pink color. Now there are many different indicators that change colors in all sorts of various pH ranges. It would be impossible to list them all. You can see phenolphthalein down there at the bottom, colorless, colorless, colorless pink. But there are tons of other ones, like bromophthalein blue is very common. Universal indicator is what's used in pH paper. There's a ton of different ones, and choosing the right one is something that, chemists deal with every day, but we're not going to talk about that in this class. So, titrations. Titrations are based on acid-base neutralization. So in a neutralization reaction, the idea is we have hydronium from an acid and hydroxide from a base. That hydronium is going to give up one of its protons to the hydroxide. That's going to leave us with two water molecules, which we know water is neutral. Now, we can look at a simplified version of this, where instead of dealing with hydronium, we're just going to be dealing with that proton H+. So that H+ is going to lock on to that OH- and produce just one water molecule instead of two. It's the same neutralization reaction, just a little bit simplified. Now, titration is an analytical method for determining the unknown concentration of an acid or a base by reacting it with a known volume of a solution with a known concentration. So there are two parts here. We're going to use a burette with a known concentration of, in this case, base. So remember, a burette is a piece of equipment that's used to measure how much liquid is dispensed. So we're going to be dispensing some of that base into an Erlenmeyer flask, which has an unknown concentration of, in this case, acid. Now the acid and base could be flipped, it doesn't really matter. Just one of them is an acid, one of them is a base. So in my flask, I don't know my concentration of acid, but in my burette, I know my concentration of base, and I can figure out how much volume I'm going to dispense because it's in a burette, which is used to measure. So as the base is added to the acid, neutralization is going to occur as the H+ and the OH- combine to make water. So here's another version of seeing this. You can see in the burette we've got all these Na pluses and OH minuses, and then in my acid I've got H pluses and NO3. So the OH minuses from the base will react with the H pluses in the acid to form water. Now the Na pluses and the NO3 minuses, they're not going to do anything in this case. They're just going to keep floating around in solution. It's the OH minuses and the H pluses that I care about. So the pH of my unknown acid solution will slowly rise as the base is added, right? I'm neutralizing that H plus. So as the concentration of H plus goes down, the pH will go up. So eventually, the amount of H plus and OH minus will be equal. This is a very special place in our titration. We call it the equivalence point. The equivalence point is the point in a titration when the moles of H plus equal the moles of OH minus. So the solution will be neutral, pH 7. Now, there's one other point that we need to talk about called the endpoint. So, an indicator is used to determine when the equivalence point has been reached. So, we're eyeballing this based off of color. So, the endpoint is when the indicator changes color because the equivalence point is reached. Now, some of you might be thinking that's redundant. They mean the same thing. Endpoint is equivalence point. Well, ideally, yes. The endpoint is the same as the equivalence point. That's what we want, right? We want the indicator to change color when we've reached the equivalence point and we stop. The problem is nothing in lab goes the way we think it will, so sometimes we have experimental error, right, where we don't see it or we go too far or we don't go far enough or it's just not good enough, where the endpoint is not exactly the equivalence point. So in chemistry, we define both because it's such a problem for us to get them to be the same. So what do we do with this information to find out what the unknown concentration was? So we have talked about before rearranging the definition of molarity to solve for moles. Now molarity is moles over liters. Remember this triangle we've talked about before. So the number of moles, if we were to cover this up, is the molarity of the solution times the volume. So at the equivalence point, the moles of H plus are equal to the moles of OH minus, which means the amount of the acid is going to be equal to the amount of the base. So on one side, I've got the molarity of the acid times the volume of the acid, and on the other side, I've got the molarity of the base times the volume of the base. Notice this simplifies down to moles of H plus from the acid. This side simplifies down to moles of OH minus from the base. So I've got molarity times volume of the acid equals molarity times volume of the base. This looks very similar to the dilution equation. Remember, M1V1 equals M2V2. The only difference is instead of 1s and 2s, I've got acid and I have base. And the math works out exactly the same way. I just have to define which one's my acid and which one's my base. So here's an example. It says 42.5 milliliters of 1.3 molar KOH are required to neutralize 50 milliliters of HCl. Find the molarity of HCl. So I'm going to create myself a little box here. And I'm going to start by talking about the acid. So my first step is deciding, okay, well, which substance is the acid? I have KOH over here and HCl over here. Now, I know from my definitions of acid and bases that acids are going to be H plus donors. So here, the HCl produces that H. This is my acid. So when I want to know the molarity, well, I don't know that, right? That's my X or my question. But the volume, I do know. It's 50 milliliters. In my next box, I'll look at the base. The base is going to be the KOH, right? That H plus acceptor. So the molarity of that base is 1.3 molar, and the volume is 42.5 milliliters. So I'm going to plug this into my equation. I've got my acid on one side and my base on the other. So I've got X times 50 equals 1.3 times 42.5. Some of you might have noticed that in that triangle on the last slide, it said molarity times liters. Well, that's true for the definition of molarity, but the great thing about using this equation is, just like dilutions, the units of volume don't matter as long as they're the same, because they are going to cancel out in this equation. So I can leave it in milliliters, I don't have to do any conversions there. So when I solve this, I'm going to start by doing 1.3 times 42.5, and then I divide it by that 50. So when I find X, I get 1.1 molar HCl. Alright, go ahead and pause the video to work on practice number 6, and when you are ready, unpause and we will go over it together. Alright, hopefully you guys didn't have too much trouble here. I'm going to start with my box. We're going to look for our acid first. So it says 56.7 milliliters of 2.7 molar HBr. Oh, ding, ding, ding. I have an H. So that is my acid. I know its molarity is 2.7 molar. I know its volume is 56.7 milliliters. Next, I want to find my base. So it says that amount is required to neutralize 25 milliliters of NaOH. Find the molarity of NaOH. So I don't know my molarity. I know my volume is 25 milliliters. So when I plug in here, I've got 2.7 times 56.7 equals x times 25. So I'm going to take that left side, divide it by 25. I get 6.1 molar NaOH. Okay, so our last section is going to be on experimental information, the reality of actually performing these titrations. So the number one problem we run into is reading a burette. Burettes have 0 at the top, so that you are measuring the amount of liquid that has been dispensed from it, not how much is in it, but how much you have let out. So when looking at this burette here, a lot of people want to tell me it's 24.55, right? They'd like to see 24.55, but that is incorrect. You should be reading burettes from the top down. Right, so you should actually be going from 23.12345. So it's 23.45 here at the meniscus, not 24.55 milliliters. The other thing we need to talk about is diluting an acid. So the dilution of an acid, adding water to an acid, is extremely exothermic. It produces a very large amount of heat very quickly. So if you add too little water while you are diluting an acid, the heat has nowhere to go but into the glassware. And what happens is when glass gets too hot too fast, it'll shatter. So you're going to end up shattering your glass and you end up with acid over everything, and that's just a really bad situation. So to combat this problem, we always pour acid into water, not water into acid. That way you always have enough water to absorb the heat, and you can stop if it starts getting too hot too fast, right? And kind of gradually do it. So the mnemonic we have to remember this is be like an otter, acid into water, which is kind of funny. I imagine little, otters jumping into the water, and it's a great time and all that. So be like an otter, acid into water. Alright, that is all I have for you guys today. This concludes our lesson on neutralization and titration. I will see you next time.